Welcome back, AP Statistics students. We are looking at lesson 12.2, which deals with transforming data to achieve linearity. And really what that means is if we have data that is curved, we need to transform it, we need to straighten it out. And we're going to look at all of the objectives over there. We're going to look at how we can use transformations involving powers and roots to allow us to create a linear relationship between two variables. We're going to make predictions with least squares regression lines and evolve transformed data. Use transformations really, and one big thing is logarithms. We should remember those from our other math classes. And we're going to look at how we transform with those as well. So this is going to be the focus of the video. We're actually going to cover everything in this video. So let's begin. First off, let's remember what we know. And when we dealt with least squares regression lines before, that was back in chapter 3. And we had two variable data, and what happens is what they showed a curved relationship, we could not write a least squares regression line for that. What we're going to do now is we're going to look at what do we do with those curved relationships? How can we create a least squares regression line, linear, with something that's curved? That doesn't quite make sense. So what we're going to do is we are going to straighten out the data. We are going to linearize that non-linear pattern. So it's going to be curved, and we're going to do some operation on it to straighten it out. And once we do that, we will now have a linear pattern, which means we can use a least squares regression line. Y hat equals a plus bx. So once the data has been transformed, we can now use that least squares regression line equation, that transformed one, and we'll make predictions with that. Now what happens is, once we have that, if conditions are met for regression inference, we can estimate confidence interval or test a claim, significance test, about a slope of the population. Remember that true slope of the population we have used before, beta, using that transformed data. So we're going to be looking at logarithms, you might look at square roots or other types of operations to help us out in order to linearize nonlinear data, straighten out curved relationships. So let's move on to the next slide. So what does it mean to linearize a nonlinear relationship? And so if we look at this, what we're going to do is a very basic example first. And this one has pizza. We have a diameter of a pizza and we have the area of the pizza on the x and y axes respectively. So if we look at this, this is the graph if I have a diameter of a pizza and we are looking at the area of that pizza, and that is a curved relationship. We can see here that we have a curved line along these. And what we want to do is we want to figure out, okay, if this is a curved line, is how do I straighten that out? And, well, let's think about the equation. Area formula is area equals pi, it's r squared. Well, we're not looking with r, we're looking at diameter of the pizza. So that would be area equals pi times diameter over 2 squared. And I'm going to make it look like it's pi, I'm going to bring the 2 squared to the bottom, make it a fourth over there, times d squared. So you can see right here that that is a quadratic function. D squared, y equals x squared, it's quadratic, d squared, our input is quadratic, it's not linear. So the question is, how do I linearize something? So linear form would be, I'd have to have some coefficient a plus bx. That would have to be what I have to get that linear function. Well, I have a d squared, I need to make it a d. Well, the way I do that is I'm going to square root both sides. So the square root of the area is the square root of pi fourths times the square root of d squared. Let's see, square root of pi, square root of 4, square root of d, and that's really what the square root of a is. So I transformed it, so now it's linear. And we can see that's really what this is showing you right here. I took that same information, I kept the diameters, the x-axis the exact same, but I changed the y-axis to be the square root of the area formula. And notice that is now a linear pattern. So I can write a least squares regression line to show this pattern. That's actually a lot better. So the original relationship was curved. So what did I do? I straightened it out. I transformed it to become a linear function, and then I can use a least squares regression line. That's really what we're doing in this lesson. So in this next part, we're looking at how to transform to achieve linearity, and I'm showing you the 3 scenarios. We have power, exponential, and logarithmic, and I'm giving you the coordinates of these. Log x comma log y, or of course natural log x comma natural log y. That would be a power function. An exponential function would be x comma log y or x comma natural log y. And a logarithmic would be when you are dealing with y equals log of x. So log of x is the x value, the input, the observed value, the explanatory response, and then y is going to be what we're looking at for the predicted. So it may look a little weird with just these. We'll come back to this and we'll look at all of these with functions. And that's kind of what I'm showing you with under this big black area right here. And I'll undo it all at one time. We'll talk about it in pieces. If we want to make a prediction, what we want to do is we want to have the equation, have the prediction equation. After we transform the curved data to make it linear, we are going to then plug in the observed x and solve for the predicted or the expected y. And I'm going to start off with a power function. And so notice when you have a power, and we'll come back here, is I'm using natural log. I'll also show the log. The y coordinate is natural log of y. And so I'm dealing with that. I have the predicted of the natural log of y equals a plus natural log of x. And I have just some random numbers that I threw in over here just to help us out. And I'm going to always use the 3 plus 7 natural log of 2 or the 3, 7, and 2 for each one. And so if 3 and 7 are my a and my b, well, sorry, 3 and 7 are my a, my b, and 2 is my x, and I plug them in, I'm going to get 3 plus 7 natural log of 2 equals the hat ln of y. So ln of y hat. Well, all of this right here is a perfect scenario for us to just kind of type this into our calculator and get 7.852. And so we have to remember, how do we solve with ln of y equals 7.852? Actually, we'll say it properly. ln of y hat equals 7.852. Remember, your base is e for ln, so e is the base, 7.852 is the power. So then y hat, we transformed it, equals e to the 7.852. Well, if I have log, it's the same exact idea. Again, I'm using the 3 plus 7, in this case log 2. This can be typed in the calculator to get about 5.107. Remember, the base for log is 10. So log y hat equals 5.107. So 10 to the 5.107 equals y hat. That is if we're dealing with power. Again, we're looking at a lot of algebra skills here. So if it's exponential, it's kind of like this. You have ln, natural log of y hat, equals a plus bx. And we plug in the information, again, 3, 7, and 2 again. Well, if I look at that, again, I could say that's 17. So natural log of y hat equals 17. My base is e to the 17 equals y hat. Same way again for log of y hat. You have to remember the base is 10. We have the same idea. You get 10 to the 17. This is just showing you how we're going to work with it. It's our algebra skills once we create that transform function. Even if it's a logarithmic function. Y hat equals a plus ln of x. And we look at this, well, my ln of 2, so 3 plus 7 ln of 2, there's my y hat. Well, y hat's already solved for. It's not, there's no log out here or anything like that. It's all by itself. We're good to go. Same thing, well, if it's log. It's all set for us. So this is really the algebra, and I kind of just wanted to go over briefly what we're working with for the setups to show you it's not too intimidating once we get the structure for a linear equation. Once we do that, we just plug in and we always solve for y hat. That's the big thing out of these 6 examples for you to understand. Always solve for y hat after you plug in the observed value. All right, so the next one is we're looking at here is a prompt that talks about, hey, go fish. Imagine that you've been put in charge of organizing a fishing tournament in which prizes will be given for the heaviest Atlantic Ocean rockfish caught. You know that many of the fish caught during the tournament will be measured and released. Oh, that's so nice. You are also aware that using delicate scales to try and weigh a fish that's flopping around after you get out of the water in a moving boat, it can be really hard and not very accurate. So it's going to be much easier to measure the length of the fish while it's on the boat, and then we can use that to kind of predict its weight. So what you need is a way to convert the length of the fish to its weight. So we have all the data there, the length and the weight of some fish that are caught in this case. We have a scatter plot. And so we have the weight on the y-axis, we have the length on the x-axis. I could see right here that this is a curved pattern. It's not linear. That's not good. And so I have to realize is that this curved pattern is not good to create a least squares regression line with. I have to straighten it out. Now, that's where we're going. I want to talk about a couple things here first. One big thing is I took all those numbers and I inputted them in the NumWorks calculator, and I created the regression, and this is the information I got. If I look at this, and I want to focus on one part, is look at this R. R is 0.9461036. You may go, man, that's a strong R. That has a strong positive linear relationship. However, let's look at the residual plot. The residual plot of that data, so we have the least squares regression line there, and I created the residual plot in NumWorks, and look at that. That is a curved pattern in the residual plot. So this is back to a chapter 3 concept. R is not enough. We can't just look at R to determine whether a relationship is linear or not. We have to look at all the information given to us. So in this case, I have to look at the residual plot. And in case you forgot, there is a poster that we have that says R is not enough. And we have the examples that show you. So I wanted to kind of talk about that on this slide, is that this information is curved, but if you were just to type the numbers in and you may go, oh, look, the R is pretty strong at 0.946, it's a curved residual plot, so it's not going to quite work for us for a linear relationship. So we're going to have to straighten it out. So we are going to use a power model in order to straighten out the data, straighten out the curve. Now there's two transformations we could do here. We could look at it by cubing our x values. And the reason why we would cube is because you can see here, what are we measuring? Length is 1 dimension, measuring the fish. To predict volume, which is weight, 3 dimensions. And so really in this case, y equals a times x to the b, weight equals a times length cubed. That's one way of doing it. So that's really what this one is showing us right here, is I can take my x values and cube them, take the length and cube them. That's going to, again, keep the y values, the response values, the exact same as weight. And that's going to allow us to see, well, this is not perfectly linear, but I mean, that's not that bad compared to what we had above. There's a really big curve there, and I can see in this case, it's not as bad. Or the other way I could do this is I could cube root the weight. And when by cube rooting the weight, what that's going to do is that's going to allow me to keep my length the exact same. So that's another way I could transform the data. And again, take a look at that. You look at that transformation, this is not that bad. It allows us to be able to go through and see, well, that's almost linear. It's got a linear relationship to it now, approximately, better say it, approximately linear relationship. Which one's the best one to do? Well, again, the scatter plot is not enough. We have to look at everything to help us out in this case. So this is really the ways we can deal with power based off of this scenario. So moving on, we need more information than just the scatter plot. And you can see we have a computer output here, and we have residual plots. That's better information. So I could try and see which one's better. Transformation 1, length cube comma weight, or transformation 2, length comma cube root of weight. And in this case, I have my mini tab outputs right here. We'll focus on this one first. Remember, we usually do not use this part right here, the standard error of the y-intercept, the t-score for the y-intercept, and the p-value of the y-intercept. We're doing an inference procedure for a significance test. We really don't use those. It'd be fun to, though. And remember, the blue is your y-intercept, 4.066. The green, length cubed, that's the explanatory. And so we have our coefficient, 0.0146774. That's the slope of it. We have the standard error of the coefficient of the slope, 0.0002404. We have the t-score, the p-value, we have all of that. And I even have down here standard deviation of the residuals and r squared. You can look down here and look at the residual plot. Okay, looks pretty good at the beginning. I'm a little concerned about, maybe that one's a little bit further away than the others. Though if I look at it, I can look at the scaling. This goes to -50, this goes to 40. All right, so I'm a little concerned at that point. Let's look at the other one and see which one's better. And so if I come over here, same thing. I go through the process. I have the constant, the y-intercept, everything gone through. You have the length. Notice in this case, it says length. And one thing you don't realize here is I can see it here where it says cube root of weight is my y value. I cannot tell you anything about my y value from the mini tab output. The mini tab output's based off the y-intercept and the slope. So I have to pay attention to the prompt when dealing with the y value, which is why we have it written up there. So keep that in mind. And I had the residual plot in that case. Let's look at the equations for both of these. Transformation 1, remember that is where the x value is length cubed and the y value is weight. Again, we can see it right up here. And so I'm looking at this. That means my hat is weight hat equals my y-intercept 4.066. In this case, my slope is positive, so plus 0.0146774 times my x value. In this case, my x value is not length. We transformed it to length cubed. And so I have to write that down in this case. And for here, we have to keep in mind what's going on. In this case, our y value is the cube root of weight. And so when I'm dealing with this one, I don't write down weight hat. I have to write down cube root of weight hat. And then we have our slope and y-intercept. Our y-intercept negative 0.02204, slope of positive 0.246616 times my x, and in this case, my x is my length. So those are the two different equations. We have to pay attention to the y-axis and the x-axis, the response variable axis and the explanatory variable axis. And we have to know what are we working with. So that's one of the reasons why we have this stuff up here for us, is to keep in mind you have to be aware of the y. And that's the big thing I want to get from this, is that the Minitab output gives us great information about our explanatory. And it gives us the units of our explanatory, length cubed and length, but it doesn't tell us our units for the response. We have to be familiar with the prompt that we're dealing with for that one. Let's move to the next slide. So now let's use these two equations and we can kind of go through, show that they are different equations. They're different y-intercepts, they're different slopes, there's different response variables, different explanatory variables, but two different graphs, but they both try to linearize, approximately linearize the information that was curved. So what happens in this case is a contestant got an Atlantic Ocean rockfish that is 36 centimeters long. We're going to use both models to predict the fish's weight. So I have the two equations, and really what's going on in this case is we're going to plug 36. But in this case, remember, you go back above, it was length cubed. So I have 36 cubed. For transformation 2, it is cube root of weight hat, and length is the x. So I just plug in 36 here. And what I need to realize in this case is what's really going on. What's going on here is straight order of operations on the right-hand side. If I were to plug the numbers on the right-hand side of the calculator, I would get weight hat equals 688.9 grams. Well, that's what I'm trying to do. I'm trying to predict the weight. I'm done with that one. However, on this side, when I go through, I have to keep in mind, when I do order of operations, that 8.856 is the cube root of weight hat. That's not weight hat. What I need to do is I need to cube it, both sides, to get weight hat. So that's where the algebra for solving equation skills come into play. So that's really what we're trying to focus on, is get the equation and then how do you solve for the predicted variable based off of what operation is being done to it. Remember, S is the standard deviation of the residuals. So we have the computer tab output. This one's 18.84 something, and then this is 0.01246. So our transformations, predictions of the weight using this model will typically vary from the least squares regression line by about, I'm going to say 19 grams. Predictions of fish weight will typically vary from this model, using this model from the least squares regression line by about 19 grams. And the other one is predictions of the cube root of fish weight using the model will typically vary from the least squares regression line by about 0.12. So that one's a little bit different. That one says cube root, while the other one here says fish weight. So notice those are our variables. This is weight, this is weight. This is cube root of weight, this is cube root of the fish weight. So again, we have to be careful with the notation, what is linked to our response variable when making some of these remarks and writing some of these interpretations down. All right, let's go to the next slide. All right, so we have here transform with powers and roots. Here's what we've done so far, is we saw that there are relationships that may require a power model for us to do, the form y equals a x to the p power. And we have two different strategies that we dealt with. We dealt with the idea of taking length cubed comma weight, so x to the p comma y, or we looked at the example of taking x comma the pth root of y, or in this case length comma cube root of y. Now in this case it wasn't that hard for us to do because we are aware that when we're looking at this that volume is 3 dimensions, length is 1 dimension, so we could easily say, well, we're dealing with a cube model, something cubed. That was pretty intuitive if we understood dimensions. Sometimes it's not going to be intuitive. Sometimes we're actually have to involve some thinking, and we can't just guess random numbers like crazy trying to get a power model. So one way we can help us out in the future is to take logarithms and use those to try and transform the data. Then we won't have to randomly guess a bunch of just different powers or roots to make the data approximately linear. So that's what we're going to focus now on this part of the video is the power model really primarily meant to get us used to the idea of the structure and how the equations are going to be set up and how the solving is going to work. Now we're going to look at how logarithms can do that, and the same idea, how can we solve for predictive values based off of logarithmic or exponential or power, we've already done power, for equations. So let's go to the next slide. So some things that we should keep in mind with properties of logarithms. We have the multiplying exponents, x to the a times x to the b equals x to the a plus b, inverse property of logarithms, and the power property of logarithms. We have all these properties that we've discussed in Algebra 2 classes or pre-calculus classes. We're now going to use those a little bit, not as much in depth, when we're trying to look at the equations. So we see 3 graphs down below. Again, I showed these based off the coordinates previously in the video of what a power setup looks like. That's the one on the left. You have in the middle, you have an exponential, x comma log y or x comma natural log y. Or you have a logarithmic, log of x comma y or natural log of x comma y. Those are the ways we're going to look at it. So those are the graphs we have down there, and we've already looked at power, so we're going to focus on the other ones for the rest of the video to help us out. So remember the idea of logs and how we solve with logs and equations. That's what we're going to focus on. So we've already looked at how not every relationship is a power model, that sometimes some curve relationships, they might be exponential or logarithmic. And so a logarithmic model is of the form y equals a plus b log x. And we're going to look at that. And one thing we're going to keep in mind is how is that created for us? And so we have right here a y equals a times b to the x. And what I'm going to do is if I want to solve for x, that's algebra for us, I'm going to take the log of both sides. So, but I have the log of the quantity a times b to the x power. Well, I can use my property log that involves log of mn, that quantity, that could be expanded into the log of n plus the log of n. I'm going to do that in this case. So I have log of y equals log of a plus log of b to the x power. But wait a minute, we don't like that power there. We want to bring that down using our power property in here. And so log of y equals log of a plus x times the log of b. You may go, well, there's a lot of logs on that right-hand side. Sure, but I want you to realize something. B is a constant. So this right here is going to be a number. And so I'm going to have some number, let's just make it 3.7 times x. Well, that's 3.7 is a slope then, isn't it? 3.7x, mx. Wait, log a, if a is some number, log of a will create a constant as well. So we'll just say log of a and we'll make it 4.1. You know, 4.1 plus 3.7x, wait a minute. That's a linear equation on the right-hand side. That's perfect. I have a slope and a y-intercept. But then I could transform that to figure out what my predicted is. So really that's kind of what's going on for us. Is that the reason why it works is if we go through and look at what would a and b be when you plug the values, they'd be constants, you create a slope-intercept form equation on the right side. And we can use that to help us out. So this is if you're looking at a logarithmic model. And so you can see on this slide, I've already talked about how if a and b are constants, what's going to happen, and how it creates a linear model that we're dealing with relating the exponential of x to the transformed variable log of y. One thing to keep in mind, a lot of words here, but I really want to focus on this bottom part is we are trying to do this. We are trying to obtain a corresponding prediction for the response variable, which means we have to undo any of the logarithmic transformations to return the original units of the measurement. And we are going to do that based off of the idea of how logs work. And so again, back from your algebra classes, log of a base, so log base b of a, b is my base, equals a power. So log base b of a equals x, b is my base, x is my power, so b to the x equals a. We're going to use that to help us out with some of our solving as we go through. But the main idea is we have a transformed equation which allows us to create a linear pattern, but when we're solving for the information, for the predictions, we need to undo the operation to get the actual units we're working with. So an example to help us out here is Moore's law on computer chips. Now this is a law. Gordon Moore was one of the founders of Intel. He predicted back in 1965 that the number of transistors on an integrated circuit chip would double every 18 months. And they call this Moore's law. And one way to measure the revolution in computing was using that. And so here are some dates. They're a little bit older, it ends in 2010. But you look at the data here and you see the values, years since 1970, and then transistor numbers on the y-axis. So my explanatory is years since 1970. And then my response is the number of transistors in the integrated circuit chip. And we can see all those values. Again, if I look at this scatter plot itself, this itself is not a linear pattern. There's no way that's going to be linear. Doesn't work. I also took those numbers, I put them in numworks, create a residual plot, and you can see the residual plot has a curve pattern. It's not going to work. You can see, by the way, and there's r and r squared. Not that good as well. So I'm looking at all the information. So that's Moore's law. Well, if it doesn't work as a linear pattern, I have to transform it. And so we are going to transform it, and what we're going to do is we are going to use natural logarithm, log base e or ln, of the number of transistors. So in other words, we are going to take the ln of y. Y is the number of transistors. And you can see that on the y-axis here. You're looking at the natural log of the transistors on the y, the years since 1970 on the x. So that is my explanatory, years since 1970. My response is no longer transistors. My response is natural log of transistors. And if I do that, look what happens. The data, it's not perfectly linear, but that's a lot better than what it was before. So if I use it, it's going to be a better predictor for what we're dealing with. So what we're looking at is an exponential model. We're looking at where our x stays the same. Our ln of y is going to be the response variable. And we're going to use that, and we can see it's roughly linear. So our x is years since 1970. ln y is ln of transistors. And the scatter plot of ln transistors versus years since 1970 has a fairly linear pattern, especially through the years 2000. So an exponential model would be reasonable in this case. Hey, you know what? When we took the natural log of the y and we kept the explanatory the same, that is a roughly linear pattern. So you know what? This model is reasonable to use. So we have a Minitab output for part B. And Minitab output, we have give the equation of the least squares regression line. Be sure to find any variables you use. Okay, so let's look at what we're going with here. We have our slope row, and we have our y-intercept row. We have the information that we don't need, or really we don't use. We don't use these, and we're not going to use the r-squared adjusted. I'm not going to use the standard error coefficient of the y-intercept. All right, so there we have it. What do we do? Well, I can see my year since 1970 is based off my slope. So my slope is 0.36583. My y-intercept is 7.0467. So I can see what I'm dealing with there. I'm going this direction on purpose. That's pretty straightforward. I have my explanatory variable right here, years since 1970, years since 1970. The slope that works for it, the y-intercept that works for it, straight on there. Here's where it's tricky. Remember, the Minitab output does not show us the units of our y variable, our response variable. I have to pay attention to the graphs, the prompts, whatever is given to me. The units for our y variable is natural log of y. So I'm going to say it's the natural log of transistors in the hat for everything. That is the equation. So we have to be careful. That's the big focus here. It's easy to get the y-intercept, the slope variable units, the numbers for those, because they're straight there in the Minitab output. the response variable is the one we need to focus on when we're looking at the graphs or we're looking at the prompt to see what are we really dealing with here. We're dealing with natural log of transistors. So then I have to use that for my response variable. So that's the focus of part B, is keep in mind, it seems like I'm saying this a lot, right? The units of your response variable. It's not be able to be seen in the immediate tab output. You have to look at the graph or you have to look at the prompt. So now we're going to use our model from this part B to answer the question to figure out predict the number of transistors of an Intel computer chip in the year 2020. So natural log transistors, we had all of our information before. So again, there it is. If we want to predict 2020 is 50 years after 1970. So I'm going to plug in 50 for years since 1970. Well, if I look at the right-hand side, this whole entire thing could be done with order of operations and get 25.3562. Here's what this means. It means the predicted natural log transistors hat, the predicted response variable, equals 25.3562. But my predicted response variable is not, transistors hat. It's natural log of transistors hat. I have to get rid of the natural log. And so remember, natural log has a base of E. So E is my base, 25.3562 is my power. By doing that and converting to exponential form in that case, I now have transistors hat. And by doing that in my calculator, I get about 1.028 times 10 to the 11th power. So here to here is the big process we have to keep in mind. When we create the least squares regression line with transformed information, our response variable was natural log of transistors hat. I don't want to solve for that. I want to solve for transistors hat. So I have to undo this natural log in front of it. And the way we do that is by converting to exponential form. So that's the first part we're looking at. So looking at part D here, we have a residual plot for this least squares regression line that we had in part B, where we had the natural log for the y, and I want you to keep in mind this is a new residual plot. In this case, our year since 1970 is our explanatory, but our response is natural log of transistors. So we need to keep that in mind still. We're still dealing with that idea. And so the residual plot shows a distinct pattern. Oh, that's not good. Can we see a pattern? It doesn't look bad. It doesn't look bad right here. This is pretty good, but oh no, look at this. You have a distinct kind of pattern there. We don't like that. So it's going from positive, negative to positive again, moving left to right. But the residuals, they're small in size. So you could see, man, look at that curved pattern. But look at this. Look at the residuals. Those are pretty small numbers when we're dealing with it. Also, the scatter plot of transform data is much more linear than it was before. So you know what? I'm comfortable with doing it. I don't like that there's a curve pattern in there. It's going from positive to positive again. Looks like it's about to keep going down to negative again. I'm starting to see a pattern there. However, if I look at those residuals, they're pretty small. I'm going to proceed with caution with this. So this is kind of outlining is, does the residual plot allow us to use our natural log transistors hat equals A plus B, in this case, year since 1970. In this case, I'm okay with it. It's not too bad. You can pause this video right here to read the Powers model again screen. I'm just going to jump right into the next example, which deals with what's a planet anyway. And so we go through this whole process, and you can see that in 2005, a team of astronomers discovered what appeared to be a new planet in the solar system. They originally named it UB313, a potential planet that is bigger than Pluto, and talks about the distance. It goes all this. Could this new body, is now called Aries, be a new planet? At the time the discovery was made, 9 known planets. Did you hear about Pluto? It's messed up. No longer a planet. Here are the data. We have all the information on the side. And one thing I want you to realize is the first thing it says is describe the relationship. That's CDOFs. And, well, what is CDOFs? Well, we have the nice little poster for that. Remember? Context, direction, unusual points, form, and strength. So I'm going to have to write what that is. So context, I'd rather start with context first. So the relationship between distance from the sun, astronomical units, and period revolution years appears to be a strong, positive, curved relationship. So if I look at this, it does look a little bit curved in that case. It's positive. I have that. Oh man, it's curved. I can't do a linear regression line for it. Darn. So what do we have next in this case? Well, in this case, I have two different graphs for us. I have one where I have distance comma natural log a period, and the other I have natural log of distance comma natural log a period. These are two least squares regression, two scatter plots, transform data. Which one looks better? Well, I can still see there's a curved pattern here, but look at this one. That's roughly linear. That's not bad. So between the two, I'm going to probably choose the one on the right. I'm going to use natural log of distance comma natural log of period. So the scatter plot of ln of period versus distance y versus x, it's clearly curved on that left side. And so an exponential model would not be appropriate for us to use. However, by doing natural log of period, y, versus x, natural log of distance, that has a roughly linear, strong linear pattern, so a power model would be appropriate in this case. So between these two choices, I'm going to use this one, which would be a power model. So we have a Minitab output. Again, let's pay attention to the Minitab output for 1 second. Remember, this is our slope. This is our y-intercept. What don't we use? We don't use the information here very often, and we don't use the r squared. Okay, there's information. However, be mindful. We can see our explanatory variable right here is natural log of distance, but the Minitab output does not show me the units for my response variable. I have to keep in mind what we said it was. The response variable is natural log of period. So I'm looking at the equation natural log of period hat. Mindful of the units for the response variable. It's probably like the 72nd time I did this in the video and said that. So we have to keep that in mind. And we have the rest from the Minitab output. Straight from the Minitab output. We have our units, our 1.49986 for our slope, our 0.000254 for our y-intercept. And so this does allow us to say natural log distance, natural log distance. That's good for us. However, the response variable, we have to look up above to help us figure it out. Use your model to predict the period of revolution for Aries, which is about 102.15 astronomical units from the sun. Show your work. So we have our equation from the previous part. What we're going to do is we are going to plug in 102.15 for the distance. We're still taking the natural log of that distance. So I have to keep that in mind when I'm looking at the equation. And when I type this whole right side in my calculator, I get 6.939. That's not the predicted period. It shouldn't make sense either. If it's further away from Pluto, that's not how long it's going to be. That is the natural log of period, the predicted of the natural log of period. I have to solve for predicted of the period of the revolution. So what happens is I'm going to use my base, which is E, and raise it to that power. So E to the 6.939 power equals the predicted period hat. And type that into my calculator, I get about 1,032 years. Now that makes more sense if it's further away than Pluto is. So the idea, again, solving is not just plugging in your calculator and getting the number now. Because if I plug in the calculator and get the number, that is not always the predicted value we're looking at. I have to be mindful of the units of the response variable. Again, 76 time now, right? That's what we're looking at in this case. So we're trying to make sure we solve for the right variable. We have to undo any of the operations on the response variable to help us. And the last part, if we look at the residual plot of that equation, and keep that in mind, this is the residual plot of this equation. What do you notice? If I look at that equation, I go, ooh, man, there is a curved pattern there. Aries value for ln distance is about 6.39, which would fall at the far right of the residual plot, where all the residuals are positive. So if you take a look, if I look at this, I want to know, is my prediction too high or too low? I follow it up. It looks like it's going up. The pattern is this way. So if my value is 6.939 in this case, that is to the far right. I'm thinking in this case, that means I am under predicting because my least squares regression line is right there. And that is the prediction, but there's a chance with that pattern that the Aries is going to be above it. So the actual, the observed, is above the predicted, the least squares regression line, so my prediction is too low in this case. All right, so that's lesson 12.2.